Waterloo first, like me, and then professor in Southampton. So he's gonna tell us about NMF related stuff.
I'm recording. Yeah, then they can download later. Okay, I can start now, right? Okay. So actually, the board is just half of the story. I have still a lot of things, and I cannot copy everything. Too tired. I mean, and then I also didn't mix the slides. Just too busy anyway. And then, so let me just get started. Okay, so today I'm going to talk about some funny thing. Okay. The reading panel is this. Okay, but later on I'll move here. This is the most important panel. But let's start from here. And to make it easier to read, I will move this down. So now let's introduce some notation. So okay. Just set up, I will consider all the X matrix M by N matrix. So N columns, M rows, okay? And then I will use column notation. That means the data is just one column. So every column here, I use a label. X subscript means column, X superscript means rows. Because I'm not going to talk about how I update H in the NMF, so I think I'm not going to talk about it. Okay. So here's the first notation, that is this thing. What is this thing? Matrix X, I take PQ norm. Okay, if you open the book, the definition is like this ugly thing. Okay, I don't care. What's the meaning? The meaning is, for each column of X, you take the P norm. And then, all P norm gives you a number, right? Then you have N columns. So you have P numbers. I stack all P numbers into a vector. And then this vector, I take the Q norm. So that means column P norm, then resultant row Q norm. Okay, so this is PQ norm. Here's some example. If P norm is 2 norm, that means what are these things? It's the L2 norm of each column. And then if my Q is 0, then I have this thing called X20 norm. It's exactly what? Number of non-zero column in X. And this has some application, okay? And today I'm going to talk about 2-1 norm. This has other name called group lasso, okay? But I'm not using group lasso, okay? So let's review what the heck is this. Every column, let me repeat, every column take 2 norm, and then the resultant thing take 1 norm. So the expression is like this. Every column take 2 norm, and then all the number you stack into a vector, and this whole vector take 1 norm. Here's the funny thing. Since norm is always larger than 0, is non-negative, therefore, you don't need to care about absolute value. So this thing can be written as just summation. So this is simple, right? Okay, so this is the thing. And here's the thing. If I use this as my optimization model, then this exists because this is called group lasso. Okay? But I'm not doing group lasso. I'm doing something called sum of norms. What is sum of norm? Short form is SON. It's a clustering thing. So sum of norm of a matrix is the same as you take P stands for pairwise difference of that matrix, and this pairwise difference means all the possible pairwise difference, and after you take this, it gives you a very big matrix, and you now do the PQ norm on this new matrix. So for example, I will start with 2, 0. So sum of norm 2, 0 of a W is the NMF W. It's like this. It counts the number of unequal pairs of the columns in Wi and Wj. Okay? And now if I do 2-1 norm, it is the same as, well, what's the 2-1 norm? 2-1 norm is all the columns, I take the 2 norm, and then all the resultant number are stacked together, and then take 1 norm. So now I have the sum of norm, which basically I take a P. P means all the pairwise difference, so I have W1 minus W2, and W1 minus W3, W1 minus W4, all the Wi minus Wj, and then what? I have a bunch of 2 norms. I stack them, and then I take the 1 norm. So this is the same as all the Wi minus Wj, I not equal to j, take 2 norm. Of course, you can also say I take all the ij. If Wi and this is also Wi, of course they give me 0, but this is bad, okay? And or if I use graph, it's the same as I take the Wi minus Wj for all the ij in complete graph. K, okay? KR stands for complete graph. What is this R? R is like number of columns in W. And in this talk, I'm going to say that I don't know what is this R, but I don't care. I just set this R as big as my data size. Okay? And then here's a recap. If your graph KR is complete graph. It has this number of edges. Okay, I have a figure here that I will explain it. Because this is r times r minus 1 divided by 2, and in big O notation that means r squared. So in other words, this guy have r squared number of terms. This r squared is a big deal. Why? Because the goal of the whole talk is I want to do something to estimate the rank of the non-negative NMF. And I don't know the r. I'm going to use the r as big as my m. That means this will have m squared term, which is very big. It's bad. But unfortunately, I will tell you some bad news later. And what the heck is this thing? This thing is called sum of norm. Of course, people claim they invent this in 2005, whatever thing, but actually this thing is a century old. It's called Fermat-Tortorelli-Weber geometric median problem. What the heck is this? So it's like this. There's a story. Somebody, some lady want to clean the clothing in the Middle Ages, and then they live very far away from the river. And then after they clean the clothing in the river, they need to go to farm and do farm work, and then maybe go to the bakery, buy bread, something like that. So you have 3 points. You have 3 points. And now you decide where to live. So you want to find a house location or home location such that it's closest to this 3 under a number, a scheme. What is the scheme? It's like this. So this is 2-dimensional case. So you are given a bunch of xi, yi, like the location. In this case, I have 3 xi and 3 yi. So it's 2-dimensional plane. Your task is to find xy, here is scalar, that means number, x coordinate, y coordinate, such that this thing is minimized. What is this? This is square root of Euclidean distance. That is this thing. Okay? So this thing actually is like what? So what is sum of norm? Well, modern name since 2000 is called sum of norm. I would say this exactly is what? Fermat-Tortorelli-Weber geometric median. What's geometric median? Geometric medians mean median in terms of geometry. So this point is the FTW point. That means Fermat-Tortorelli-Weber point. That means the geometric median. This is slightly different from average, median, center of mass, centroid. If you count the, okay, my drawing is bad. If you draw the center of mass, it's not exactly here. So there are a lot of ways you can find the average. So this is called the geometric median. Okay, so these are set. So what I'm going to do? What I'm going to do is that I'm going to.
How to compute? It's iterative method. Or?
How do you mean geometric median or what?
Yeah, how do you compute the geometric median?
You ask these 3 people. I don't know. I don't care. Okay.
Because it's a convex problem, but it's not smooth.
Because what they do is doing this problem few hundred or 1,000 years ago, I don't know, but because what I'm going to do is I'm going to plug this in NMF. Then the whole situation is very different. Okay, so I am just saying that this means this term actually is not a new thing, but people in 2000 think that they make it in NMF. So now this is the setup. Okay, any question you can ask me anytime. Now I go to other board. Okay, so now I have this example. This is a little bit complicated, so let's look at an example to understand what the heck is this. So suppose I have 5 columns. X only have 5 columns. Okay, so first, imagine you don't see the bar. Okay, imagine you don't see the bar. Okay, let me explain what the heck this bar means. So I'm now going to say the following assumption. Suppose you have x, x1, x2, x3, x4, x5. And now suppose you know that this x has rank 3. Okay, rank 3. Then, if you do this thing, what will happen? My response is you will get something like this. What is this bar? You can think of this bar means I separate them into different clusters. So this is cluster 1, this is cluster 2, this is cluster 3. So cluster 1, I call it C1, C stands for cluster, have what? Have column 1. Cluster 2, I have column 2. Cluster 3, I have 3 columns. That is column 3, column 4, column 5, these 3 things. So I have 3 clusters, and this number is number of clusters. And this cluster have 1 column, so cluster size is 1. This cluster have 1 column, cluster size 1. This cluster have 3 columns, cluster size 3. Okay, these are just set up. So suppose I have this cluster distribution, okay? What will be my sum of norm to 1? Okay, so what is sum of norm? Sum of norm is basically all the ij multiply, subtract each other, right? So I can draw a table. So if I draw a table like this, what happens? Well, of course, column 1 minus column 1 itself is 0, so all the diagonal I don't draw it. And this table is symmetric, so I don't need to draw the lower half, so I don't need to consider half of the table. So actually, this is why I have a divide by 2 there, okay? And then, what is this guy? This guy is column 1 minus column 2. Well, since column 1 and column 2 are in different clusters, then of course I will have C1 minus C2. Okay, notation. C, the small c is centroid or center. Okay, so basically it means what? It means x1 will take the value C1, x2 will take the value C2, x3, x4, x5 in the end will take the value C3. Okay, let's assume this. Okay, then what about C1 and C3? Well, of course, subtract. They are in different clusters. And same for these two pair in the sum of norm. And what about these two here? Well, they're in different clusters. So I have C2 minus C3, C2 minus C3, C2 minus C3. What about the C3 subtracting each other? They are all C3, so therefore it's 0. So I have how many? I went down 1, 2, 3, 4, 5, 6, 7. I have 7 sum in this sum of norm thing. That means if I write this down explicitly, this is the notation. All the Wi minus all the Wj sum together, okay? But I can also write it like this. It will be the number of columns in cluster I times the number of columns in cluster J. These are the number of terms in each cluster, multiply their distance, okay? Which is, I just show you here, right? So this will be CSON21 of X. So this is the table, this is the algebra, this is a picture. So how do you understand this? So I have the 5 point, 1, 2, 3, 4, 5. Now cluster 1 is this guy alone, cluster 2 is this guy alone, cluster 3 is this 3 guy. So if I do sum of norm 2, 1, it's the same as I draw a complete graph on the whole figure, and I have a bunch of lines. But C5 and C, these two are the same cluster, so I don't need to draw them, they're gone. So these are the lines. How many lines there? Like this. Here's a funny thing. Suppose I don't care about this difference. Or I can say all the difference is 1, okay? Or in other words, I consider 2 0 norm. 2 0 norm means what? How many Ci not equal to Cj? Then I don't need to care about this. Then I will have only this part. This part is the product of pairwise cluster. And this thing very simple. I can say this guy is smaller than the largest cluster size. This is a constant. I can take it out. And then sum of all clusters is smaller than R. So that means this whole thing is smaller than R squared. So in other words, SON20X is always smaller than R squared. What is R squared? R is the number of columns in X. Okay. Then here's a funny thing. What will be the optimal C1, C2, C3, C4 that minimize this? Then this is the following funny thing. You have a bunch of cluster size. You can think of those cluster size as a number, a scalar. So you are given a condition that you have K cluster, C1 plus C2 plus C3 up sum to K. K is a number. You want to minimize the sum of products. Then after some algebra, okay, high school inequality, then you get the following conclusion. The conclusion is that all the cluster except one, that means cluster 1, cluster 2, until the second last cluster, all these clusters have size 1. That means only one guy. Exactly this figure. That means if this matrix X has 3 clusters, what will be the smallest combination here? It will be, there will be 2 clusters only have cluster size 1, and the last cluster take everything else. So this will make this number smallest. Okay? Then why this is good? Well, this is good because in terms of NMF, you can say that I have some component in the data that is very weak in terms of energy. Then this is saying that if I put this SON term in the NMF, it will always find it out. Why? Because you have this subtraction. If you have something that is very weak, then of course the subtract with other people, the norm is very big. Notice that this is not norm square, it's just 2 norm. Okay? And then this is a theorem. Now here's the first thing. If I'm talking about this thing, I said that this thing has R squared term because it's complete graph R squared. In the setup here, I'm going to say that I want to solve NMF without knowing the rank, and I just initialize my W and H as big as my data size. So that means how many pairs here? There are M square pair here. So this term is very, very big. Can I reduce the graph smaller? The answer is no, I'm sorry. So here's a theorem. So now it's notation. Suppose I have a matrix M. I know the true rank, I mean NMF rank is R star. And let's say this NMF on this matrix M with this rank R star gives me W star H star. So W star H star is like the global true, ground truth, ultimate truth, okay? And now suppose, I didn't talk about what is my formulation of SON NMF now, but assume I have a SON NMF with something using this thing. And then I work on the same matrix, but I work with the input rank R that is larger than the true rank. So this is the setup, and I get the WH. So this WH is not a variable. This WH is the solution from this sum of norm NMF. Okay. And now here's a fact. I'm saying, assuming I'm at the best of the best situation, that is, certain columns of this W contain this guy. So I'm saying that the columns of the true solution is somewhere inside my W from the sum of norm. Because I'm doing this and I'm using a bigger rank, actually I'm going to have duplicate, or I have some redundant thing. But now I'm saying that my W have something containing this W star. I'm assuming this, okay? Then what are you going to do? We are just going to do, well, I have this thing containing this, then I'm going to use something on here to approximate this. So I'm saying we want to use the columns of this W to recover this W star. Okay, how do we recover later? But now let's say we have a method to recover W star from W. I'm assuming all this, okay? Here's the thing. If these two assumptions holds, can we, not using all the KR column, KR edges in the complete graph to achieve this? The answer is no. The answer is we cannot use a graph smaller than KR. In other words, if you're at the best situation that you can really recover your ground truth using a bigger W based on this argument, unfortunately, you cannot use a smaller graph. You have to use a complete graph. And actually, you can use a smaller graph. And here's the improvement. But the improvement is very bad. So complete graph have R times R minus 1 divided by 2 number of edges. At the best case, you can improve this from this number to this ugly number. What's this number? So this number are all R divided by 2, R divided by 2, nothing changed. There's R here, no change, R here, no change. Now I can improve from minus 1 to minus R divided by R star ceiling. So this number can be potentially larger than 1, but the thing is, you can see that if my R star is big, this is rubbish. So here's an example. Suppose I use a 1000 rank in my W and H, and let's say the NMF true rank is 25. Then complete graph will have 499500 this many edges. That means if I use complete graph, I have this number of terms in my this summation term. And if I am at the best situation, best initialization, best algorithm, best convergence, everything the best, at best, I can only reduce from this number to this number, which I only have a 5% decrease. In other words, I cannot reduce the complexity of this complete graph in the best case. And since this is already the theoretical best case, and in practice, everything is worse than this, that means there's no way you can reduce the complexity of this thing. That's the trade-off, okay? So this is the first theorem. How to prove this graph theory? Okay. Because time, not going to talk about it, and also the board is not enough. Actually, the proof is in the paper here, but I'm not going to draw finger paint. Okay. So any question up to here? So let me recap what I'm going to do. I have introduced this funny PQ norm. Well, PQ norm is not introduced by me. PQ norm exists, but now I'm going to consider this as sum of norm, which is basically the composition of pairwise difference, and then take the PQ norm. And I'm only focusing 2, 1, and 2, 0. Okay? And then this thing has a name called this free European person geometric median. Okay? What's the physical meaning? Physical meaning is to find a geometric median in Rn. Okay? So it's like a median thing. Okay? And what's the example? Well, suppose I have 5 columns, but I have 3 clusters. Then in the end, it will give me this. Of course, you can argue, what about 1, 2, 3 is one cluster, 4, 5 is another cluster? Yeah, it's same, it's just permutation. But I'm saying that the key fact is, if I have 5 columns, more column than cluster, then if I minimize the 2, 0, in the end, there will be one cluster take the rest, and the other cluster only one term. This is a theorem, okay? And this is good. And of course, can I simplify the complexity? No, the answer is no, okay? And then, what next? Okay?
Can you, for the theorem, can you explain a bit more?
So how do I explain this? Okay. This I think the best is to discuss this offline in our meeting. The best is so the best is basically graph theorem. It's like clustering, right? So if I have cluster, so suppose I have this structure. Here's the thing. It's about subgraph, connected subgraph. 4, 3, 5 are in the same cluster, but based on this kind of connectivity, you can see that I can always find a path connecting 3 to 5. So for example, like this. So 3 will connect to 1 and 1 will connect to 5. So here's the argument. If 3 and 5 are in different cluster, that means they are not in the same shape. Then they do not have they cannot be connected. But the thing is, I'm going to use the negation of this statement. That means I'm going to prove the contradiction, saying that if they are not in the same cluster, then they not exist a path. But now I'm assuming the opposite. So then you lead to contradiction, and you prove that this is not case. Then therefore the argument is not whole. But okay, let me phrase it. It's too complicated to discuss now, so I think it's better to talk about it in offline. Yeah. But the argument is basically a contradiction, and it's like a pigeonhole principle. So you assume the best, and then you study what happened at the best situation, and you show that at best this is what you can get at the best situation. And since in all the situations it will be worse than the best, so if you bound the best, that means the every situation, practical situation, is very bad, and then therefore you get your conclusion, something like that. Yeah. Okay.
When you mean W star is in W,
W contains the column of W star.
Like the column, not,
yeah.
It's not about the cone of.
Yeah. Because I'm doing this pairwise difference, subtracting. Yeah. Okay.
But I understand if you assume this is true, then what? I mean, why do you? And how does it? So you say it cannot be true.
So I'm saying, okay, what is this? There are 3 W star here. Now let's say, okay, this is a little bit confusing. This is not X, this is W. Okay, suppose I have W, have this, and now I only have rank 3. So therefore, I only have 3 components here. So if I do this, it will give me this column, and this cluster. This column is my W1, this column is my W3, this cluster is my W3, this column is my W2, okay? So 3, 4, 5 are my W3, but I have duplicate. This is W3, this is W3, this is also W3. They all share the same column. And what is it? That means these 3 columns are exact copy. That means what? This matrix is collinear. These 3 columns are copy of each other. So what, okay, maybe I should go to the conclusion. What I'm going to do in the whole problem is, I'm going to solve this. What is this? This is NMF, okay, nothing special. I'm going to do this. This actually is the same as this. So this is better to explain. Among all the NMF possible linear combination or possible solution of NMF, I want to find the W such that the sum of norm 2, 1 is the smallest. So what does it mean? This actually is 2, 1 norm, is a convex relaxation of the stronger 2, 0 norm. What does it mean? It means among all the NMF that give me M, I want to find a W that have the smallest number of pairwise unequal pair. So this is what I want to do. And Olivia just asked, how do you get from here to here? Okay, this is actually this spot, but later, not now. So let me recap what I want to do. So basically the model is, I want to minimize fitting, subject add with sum of norm. This is what? I'm going to start with a W and H that is much bigger than the true rank. And actually I'm not going to care about what the true rank of my data. I just set the rank of W and H as big as the data size. Then I'm going to do this. And since I'm using much more columns and rows needed than I needed, so I need to enforce them to be close to each other. So this has something to do with minimum volume, but this is not exactly minimum, this is some weird thing anyway. And if let's say the data is rank 3, and let's say I have 2000 W, then by this theorem, these 2000 columns, there will be one column is the first W, the another column is the second W, and the rest of the 1900 whatever thing will be the third column, and they are all duplicate. If let's say I solve it, of course solve it. This is in a quotation mark because this problem probably is also NP hard anyway. Yeah, but I have very fast algorithm to solve this. So the idea is I want to solve this approximately numerically, then by something called proximal algorithm, which is here. Then solving this is the same as I solve this, because basically these two are the same thing. It's the same as I move these to the objective function. So there exists a lambda, there I can move it here, okay? Then solving this is the same as solving this, because the setup fulfill the compressed sensing thing that you solve the L1 norm is the same as solving L0 norm with high probability. So solving this is also solving this. Then now assume I have solution from here. Then I just do a greedy selection, I will get 63% optimal guarantee. That means what? That means if under this condition, W star is in my W. Here's the thing. That means, let's say W star is 3 columns. That means I have a rank-free NMF here. But this W have 2,000 columns. Then how do you know which 3 columns are this? You don't know. Because if you know, you solve an NP hard problem, okay? So what I'm going to do, I'm going to do greedy selection in the column here. And there will be theoretical guarantee showing that I will get 63%. That means what? It will be very likely I will get a bunch of useless columns here, but the fitting will be 63% as good as this one. Based on something on that board, I will explain soon. Any question? If no, then I will first talk about how I proceed with this. Because the argument is, I can solve this numerically. Solving this numerically, this is approximately equal. That means I approximately solve this. Approximately solve this is the same as probabilistically solve this. Probability solve this using greedy means I approximately solve this. And that's it. So this is the logic chain. So that means if I cannot solve this numerically good, then this doesn't work. Yeah. So I have established this, and that's the whole thing. So now I'm going to talk about how I solve this. And this is what? This is an NMF problem. So you have 2 blocks. One is H, one is W. Okay, in this setup, H is not important. So I'm not going to talk about what's H. Actually, in the paper, H have a condition that is in the unit simplex to make the scaling even better, but I'm not talking about this. Okay, now I'm going to talk about H. I talk about W. So here's a subproblem on W. So how do you solve subproblem on W? So the subproblem on W looks like this. I will arc mean on W. This is fitting, NMF term. This is sum of norm. All the pairwise Wi minus Wj 2 norm. Very important, there's no square here because you want sparsity, right? Because this is 2, 1 norm, okay? You want sparsity. And in fact, if you put a 2 norm here, that thing exists. It's called graph NMF, okay? But I'm not doing graph NMF. And then, what the heck is this thing? Okay, this actually is the non-negative W. Here's the thing. If I put an indicator function here saying that I'm forcing W to be non-negative, I'm sorry, this problem cannot be solved. I have to avoid using indicator function. I have to do penalty. This is penalty. What does it mean? It means if I have W that's negative, if W has something negative, then negative of this value gives me positive number, then negative will give me value increase. So I don't want that, so I have to make the function value down. Yeah, this is the trade-off. I cannot avoid this. And then you will argue, oh, you need to tune number, you need to gamma, blah blah. Yeah, come on, this NMF program, what can you do? Okay. So this is NMF NP hard. Okay. So. And furthermore, now I'm going to talk about a bunch of negative things about this problem.
So you need some precise number to recover the truth.
You are asking a good question. Okay, you asked a good question. Actually, let me tell you a very funny thing. So, let me tell you a funny thing. Actually, I put this down in the paper. I know people will ask it. So let me tell you a possible attack to my paper. Suppose I want to solve NMF. And I don't know the rank. Now you should know what is the situation. The situation is I want to know NMF without knowing the rank. I want to solve it. So it's like tuning the rank. Then you can say I just try all the rank. Then the search space of rank is all the integer. It's all natural number 1, 2, 3, 4, 5 up to infinity. Here, the search space, yeah, the search.
Infinity you can stop at n.
Okay, I can stop at n anyway. My point is the search space here is countable. The search space here is real number. And you know real number have more number than integer. So that means what? It's still good. I'm making my search space infinitely more bigger than integer. So how do I attack this? Very simple. Well, I will have to assume in practice data have hierarchical clusters, so I don't need to tune. For example, if very small lambda, then in a hyperspectral image, that means I only differentiate non-vegetation and vegetation, and if I want to classify tree and grass, I use a bigger lambda. That's very natural in data. That means what? In practice, actually in experiment, I don't tune number, I just randomly put some number, and then it works. Because in the end, it's just you run this long enough, it will work, and yeah.
Actually, it's interesting, if you start with a very large lambda, you get a small rank, like rank 2, and then if you decrease it, you will like...
Oh, that's homotopy. I'm not going to talk about homotopy.
No, that's a homotopy, like hierarchical...
Yeah. Actually, in the appendix of the paper, there is a hierarchical tree. I'm doing that, yeah. But not important, yeah. my focus is this number. So how do you apply this later? I don't care actually. But later, actually, I will talk about it. But now let's go back to this. And of course, you will argue, how do you 2 lambda? And let me tell you even worse. In order to solve this problem by using so-called proximal average, you also need to tune this guy. Oh my God, you have to tune 2 number, and not actually not 2 number. This is a bunch of terms. So if you tune this, you affect all of them. And again, this is a sum. So if you tune this, you affect all of them. Then of course you can argue, can I have lambda ij on this and then gamma ij? Yeah, you can. But then there will be extremely many parameters, more than deep learning. So no. So here's the thing. What's the negative thing of this? Here's a bunch of negative things. This problem is not differentiable. Why? Because what is this? This is 2 norm without square. So this is like absolute value. And because you see this term have a square. And if this term is 0 and if this term is 0, you have square root 0 square. You have this thing square. You know square root and square give you absolute value. So this thing is not differentiable. And furthermore, this guy is a bunch of wi minus wj, and I'm minimizing this, so I'm forcing them to be the same. So I'm forcing them to have non-differentiability and have a bunch of summation. So that means I have a bunch of this, not differentiable. This is not good. So the first one is non-proof. In the 2 norm, this is absolute value, and then 1 norm is again absolute value. I have a bunch of absolute value, and the algorithm will automatically favor this to happen. So this is stupid. The algorithm will make this thing worse and worse if it is being better and better and better. That means the better you solve this problem, the worse you have for this. This is the first thing. The second thing is non-separable. What does it mean? Well, all the W I W lumped together. You cannot say I split them. So ADMM doesn't work. Right? All other things doesn't work. The first thing, it's not proximable. I'll explain this later. This is not second order friendly. Why? This has m squared term. You try to compute Newton, good luck, okay? This is not dual friendly. ADMM introduced 3 times of Lagrangian multiplier and dual variable. This has m squared. Okay, good luck. And now then I have another m term here. So in other words, of course you can try to run ADMM. Actually in the paper I have a comparison of this method with ADMM. ADMM runs until the dawn of the Earth or the sun explodes. It's still not complete, okay? So that means Mons. That means what? Cannot run second order method, cannot run dual. You are only allowed to run what? Either 0 order method or first order method. So that's why I run first order method.
You should do majorization, minimization. We get discussed if you want to.
Okay. So now here's the thing. This is the setup. This is the continuous optimization. So let me recap. All the thing here is discrete optimization, combinatorial graph theory. Now this is the only screen that is or continuous. So what the heck is going on? I have a foreign setup. This part is differentiable. So this is the function phi that is differentiable. So I can go gradient. Okay. And then this part is a sum. This part represents this big sum here. Okay. This part is the non-differentiable part. Okay, most of you are in the workshop in Antwerp, so you probably know what the heck is. Proximal gradient descent. You have your current point. Take the gradient of the differentiable part and the current point. Multiply step size beta. Okay, now I use beta. I cannot use alpha. Alpha I've already used it here anyway. So this step size. Of course, you can say, oh, it's a step size. I 1 over L or whatever. Okay, I don't care now. So you know there's a step size. Okay. Then I'll do gradient descent. After I do gradient descent, I prox this with the non-differentiable part. Here's the bad news. This guy is a sum of function. That means proc this is the same as proc this. What's proc? It's arcmean of your thing plus 2 norm. This guy has m squared term. Can you solve it? No. Can you solve this using ADMM again? Come on, m squared term. Can you solve this using Newton's again? Come on, m squared term. Can you do this, do variable this? Come on, m squared term. Majorization, right? Okay, m squared may be very slow. I don't know. So this is very bad. Well, come on, this is NP hard thing. I'm tackling NP hard thing. What can you expect? So what to do? Here's the ultimate trick. If a problem is very difficult, yes, then you move to epsilon 4 around this problem. Hopefully, this is easier to solve. So here's the trick. I'm not going to solve the sharp equation. I'm going to solve this thunder equation. What the heck is this? This is the same guy. This is the same guy. I'm not going to solve this. I solve another function a. What is this a? A is not this. But okay, this is indirect definition. I define A implicitly. The Moore envelope of A is the same as the Moore envelope of this thing. So this is my non-differentiable part here, or this thing. I have a bunch of sharp corners. Okay, for those who are in the workshop, what's Moore envelope? Basically, you just move this, okay, right? And then now suppose I have 2B. If I have this, I add it up, so the function looks like this, right? I have a sharp corner here, so sharp corner here, sharp corner here. Everything here is just add up, so I flat line. Then I what? I just Moore envelope the whole thing. Then I will have like this. Okay, now this is not sharp. This is not sharp. This is differentiable. Then I just solve this. Okay, that's the idea. Very simple, right? Of course, this not come from me. This comes from big name. Okay, in Canada. Okay, so this is called proximal averaging. The limitation of this thing is that this kind of setup you cannot jump to infinity, because if you have something jump to infinity, how do you smooth it? This is the reason why I cannot have larger than 0. I have to use this and introduce another gamma, which is bad. Yes, but in order for this to work, I need to sacrifice this. So now I have this thing. What I'm going to do is exactly like this. So first I have gradient descent. So this is the red thing. And now I write down my red thing as an x bar. And now what I'm going to do, instead of prox the whole thing, I prox each of them and take the average. So this is like or linear interpolation or linear combination. So this is the idea. I prox each of them to phi I. That means what? That means first take gradient on this guy, and then what's next? Prox the first term, prox the second term, prox the third term, prox the fourth term, until the last guy, same prox the first, second, and then I have a bunch of prox, and then I just take average. What is alpha here? Actually, any number sum to 1. So for stupidity, just 1 over n, okay, done. So that's it. So this is the idea. What's the magic here? The magic is, if I have a solution, let me call it x the underline, under 2 line. This thing is a solution for this, right? This thing is a solution for my Funder equation. And suppose this x underline is an epsilon solution for my Funder, then I can show that this x underline is a 2 epsilon solution for my original problem. And if epsilon is 10 to the negative 16, I don't care about 2. So this is the idea. If I cannot solve this, I solve an epsilon problem near it, and actually the radius is 2 epsilon, but epsilon is very small and I don't care. Okay? And now this, and with this, what's the good news? Using this no longer smooth because you Moore it. It's still not separable, okay? Now it's proximable, good. It's still not this, but you now fix these two. Yeah, you fix these two, and with this three, you can just run this. This is still first order method. And don't forget, this sum have so many terms. This sum have so many terms. This is the best you can get for first order method. And this sum is a big number of terms. You can do second order method or whatever thing. Computer will explode, so that's why this is the best. And with all this, then now I can solve the W's problem, and I can put back to the model, and I can solve this problem. So then here's the thing. Here's now the most important thing that I have the least amount of content because of time. So now assume I have a very good solution to this problem. Let's say I have a WH that basically numerically solve this problem. Then I say that because of using proximal average, I solve this is the same as solving this, they are the same. If I have the lambda, of course. In reality, you can argue, how do you tune this lambda? And I can say even worse, how do you tune the gamma? Okay, I don't care, but let's say you tune the lambda and you tune the gamma. Then this is done. I'll have this. By the theory of whatever compressive sensing thing, this guy and this guy are the same, so I have this. Now I'm here, so now I'm here, okay? So now here's the thing. Suppose I have W and H. This is not variable. This is solution obtained from here. And let's say I'm at the lucky state that this solution is this solution. You know, for the compressive sensing, they say that if the matrix A in the linear term have some RLP condition, then you have 95 whatever percentage that this is this. Okay, that means there's a probability, but I don't care. Okay, let's say I am here. Okay, so now suppose I have WH. Let's solve this. What's the claim? My claim is some columns here are hidden here. I just don't know. Yeah, that's the problem. So I need a method from the column WH here to get the column here. What's the trick? Well, the stupid trick is, of course, you use all the columns here, but of course that's stupid because how many columns? M square column. M is much bigger than R. Then of course, if you use all the column, you always fit the whole thing 100% good. But come on, you want to find the rank, right? So you want to find a few number of columns here. So how do you find this? I'm sorry. Column subset selection itself is also NP hard. So therefore, there's no way you can do that. So what I'm going to do, I'm going to do something called greedy. So what I'm going to do, well, I have this SON term, right? I already explained in this whole board, I have a term called SON. I can use SON 1 to 1, okay? Then I start with an MP index set I, nothing. And each time I just find the column I that including this column in the index set will make my SON increase the max. So basically means greedy. I greedily select the next column such that my SON term have the biggest increment. And just put this I into my index set. And I do this until I stop, okay? Then what you will see? Well, of course you will see a very typical graph, that is, you see something like this. After a certain column, you have a corner change.
You choose the first index.
First index, empty set. You just find the, okay, good point. In the red one. In the first index, I just randomly select one. Because first index, you have nothing to compare. So I just select one. Yeah.
It's 0.
Yeah. And then, okay, this first index is actually a good point. But, okay, and then what? If you do this, you will see a graph that like this. After some corner, it does not move anymore. Why? Because actually, I can explain here. Suppose I already select this as my column 1, and I already select this as my column 2, and let's say my third column, I select this guy. Okay, what happens if I select my fourth column? Okay, so that means I have this already, I have this already, and I have this already. If I select my fourth column, that means as this guy, I'm gaining this line and this line. But since these two lines are the same as these two lines, so that means what? That means the increase in this here will be smaller than the increase here because you have already selected them previously. So that's why the slope here will be steeper. So that means what? How do I find the rank? Practically, I'm not saying theoretically. I can just look at the corner point. So that means if you do this for all the M square column, you probably will see something like this. You have some corner point, some corner point, some corner point. So basically, this is like the first R cluster. This is like everything in the first big cluster. So if I draw a complete picture, so you have a first cluster here, second cluster here, third cluster here, fourth cluster here. So this region corresponds to, you select the first guy here, second guy here, first guy here. So every cluster, you select them in correspond to this. This second segment corresponds to selecting everything in second cluster. And then you have the first segment corresponding everything in this, because after the first segment, the only thing left is to repeatedly select other cluster that you have already chosen previously. So that's why the increase will be slow. So that means, practically speaking, this corner point is the rank. Practically, I'm not saying this is theoretically true. And then we can show that, here's the thing. This SON term has a funny property that this is called submodular. Because of time, I'm not going to talk about what is submodular. And for those who want to do NMF on combinatorial side, please study this, it's very interesting. And if you want to work, we can talk about this. I have actually a lot of idea on this topic. And I can tell you, this topic is not something new. Francis Bach already played with this 10 years ago. That means this is something, not old news, this is old news, okay? And then, if you have a sum of norm, this is submodular, and SON is also monotone. What does it mean? Well, it's the sum of norms. Norm is larger than 0. That means if you including new term into the sum, it's only increase, it cannot decrease, so it's monotone. With these two in mind, then you can prove that I select whatever column W with certain cardinality, I will have this bound. What is this bound? The sum of norm value will be larger than 1 minus e power r. R is the number of rank in this W in my solution, divided by the true rank R, which I have a lower bound by 63%. So what does it mean? It means, suppose this NMF is rank 5. Of course, I don't know this number, okay? If I know this number, I already solved the problem. So suppose this is rank 5, but I don't know, but let's say I know, okay? Then how do I get the 5 column from here to here? I'm going to do greedy selection on here by 5 column. Here's the thing. Greedy means I look at all the possible good columns and then I select based on greedy and then get 5 columns. It's possible. Greedy is not good, right? It's not global optimum. So it will give me 5 columns, but this 5 column is not necessarily the 5 column here. It can give me some garbage column. But I can guarantee this 5 column under the rating of SON value. That means how this 5 column will make this number big. I can have 63% guarantee. Of course, you can then ask, what about if I replace this SON term with this fitting term? You will get the same thing. If you replace this SON term by the fitting, because it's also submodular and monotone, it's norm, right? So you will get the same thing, something similar. But I will do SON because SON is a very greedy graph thing, combinatorial thing. Naturally, people will do it. Okay, so I will do this. And here's another thing. Suppose this is rank 5. Again, I don't know the rank, but let's say I know rank 5. Now, because I don't know 5, right? I'm going to do some greedy column selection here. Let's say I select 10 columns. Then this number actually will increase to 80 something. And let me tell you a funny thing. If this is 2 rank, which I use the number R star, and this is the R, that means my estimated rank. If this R and R star have some funny number, let's say R is 10 times of R star, then you have 1 minus e to the negative 10 something, then you will get 99.99999%. What does it mean? It means, suppose this NMF have rank 5. I don't know which 5 columns are here in this. I don't care. I just select 50 columns up here. Then this 50 column will 99.99999% contains all the best 5 columns here. Of course, I'm not saying I know which 5 column. I'm just saying that 5 column is within the 50 column here. I still don't know which column. Yeah. This looks very good, right? But don't forget, this result also includes the situation. The NMF rank here is 1 million. Then if you do this, you need 1 million times 10. And you know, that's impossible. So that means what? This kind of thing is very practical if data is low rank, which is what we are doing. Good. Yeah. So that's the thing. And what's next? I have a bunch of funny pictures, and Nicola, you have seen it, and some people have seen it yesterday. And since I didn't prepare the slide, so I don't want to show the picture. But basically, the picture is like this. You have some data set. I'm just using the data on experiment to reclaim this. What? First of all, I have this. Suppose I have urban. I assume everybody knows what's urban, the hyperspectral area. You have tree, you have water, you have road, you have grass, you have soil. Then you know in the hyperspectral, water is relatively weaker. If I do SON NMF, I will get it in the first component. But if you run normal NMF by HARS or whatever thing, because water is very weak, so it will be ignored by the 2 norm. So therefore, it will be appearing only in a later stage. But if I do sum of norm, it appears in the first stage. It won't, that means the ability is it will detect weak component. Why? Because if you have weak component, you subtract with other component, this number is very big, right? So that's it. And then what's next? This is the first thing. The second thing is there's some synthetic data set. For example, there are major NMF. You know the non-negative rank. Then I have the experiment that the rank is 4. I mean the non-negative rank is rank 4, but I use a rank bigger than 4, and this will recover to the 4 cluster in the true solution. And also there's a swimmer data set that is you have a bunch of image, a person swimming, okay? And then this data set, I run this sum of non-NMF. I run a rank 100 sum of non because it's actually 110 by 10 pixels. I forgot the dimension, but I run a 100 rank. Then it decomposed what? It decomposed to 7 components. The first component is the head, the second component is the arm, the third component is this. So basically, I split the whole body into 7 different components with no mixing. And if you do ordinary NMF, what you get, for example, one component is this, and then one component is this. But if I do this, I will split all the components. Why? Why this is happening? Because left arm and left leg do not agree. Yeah, so I can do this. And what about the rest of the other component? That means the redundant, because this is not rank 100, right? So all the rest of the component will be the complement of this image. It's basically everything else but black space. And that means I successfully find the rank of this thing. And of course, I can do this on urban. And I forgot to tell you the worst thing. The complexities of this is something like this. The algorithm, the complexity, something like this. So because because my m is a space of my nm, so you can think of this, to run this, it is this expensive to run this. So in urban, it's like 1 million. So 1 million power free. So this whole thing, the reason why I do first order is because this is the only thing I can do. If you do second order, you have to make this power free. That means 18. Oh my gosh! And then need supercomputer. So the drawback of this thing is very, 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 very slow. But that's okay because I'm using speed to trade off for 63% approximately NP hard thing. Yeah. And then what's the other drawback? Of course, you need to know lambda. Then I will argue this is about parameter tuning. What are the possible future work? We can study bi-level on this, hyper gradient on this, or whatever other thing, or statistic thing on this, because whole project on this is not focused on lambda. I assume I know lambda, okay? And in the experiment, I just use a stupid lambda like 110, I don't tune it. Yeah. And that's the idea. And then what about other future project? Okay, this is for you. Do this on tensor. Tensor ring, tensor train, tensor X, tensor Y, Tucker, CPD. Yeah, we will be excited. Yeah. C'est tout. Merci beaucoup.
Any question or comments?
We can talk about it offline. Let's go to lunch.
Actually, this algorithm is funny because it's like a separable NMF algorithm actually.
Yes, actually we can talk about this later. Yeah.
If you use a volume, you get SPA instead of the sun one. And in fact, I've seen a paper that does something like this. So each time they select a column of X. Of course, in the separable case, you have X equals W. And then they select the first column with a maximum norm, and then the second one, which is the furthest away, and then the third one, which is the furthest away. So it's exactly
but for mean vault, then we need to show that it's submodular and monotone. I think it's easy to show mean vault is submodular and monotone.
I don't think it's monotone actually.
Monotone means if you add a column,
If I add a zero column, it will decrease. It will get
so that okay, then it's not the same thing because this 60V require these two. And I can tell you, the proof of deriving this is actually quite exciting. There's a one step. When I read it, I was like, wow, and then
But the second problem, this problem you have to solve at the end is called dictionary-based NMF. Essentially,
okay.
You have a big dictionary too large, and you want to select subsets.
Yeah.
In fact, I have a paper with Jeremy about this.
And we can talk about this. And so this is the thing for the discrete people. Search about this. This is very interesting. And actually, what is this? This for those I know Arno, you are like intermediate between continuous and discrete. So what the thing is this? Selecting a particular columns of W. Okay, now I'm going to talk about algebraic encoding of some combinatorial thing. So I have a bunch of W. So I have 1, 2, 3, 4, 5. Let's say I have a bunch of columns. It is same as I have a vector of 0 and 1. 1 in particular location means I select that column in the W. So since this is a 0, 1 vector, that means I'm now having a 0, 1 hypercube. So I have a cube with a bunch of 0, 1. Of course, this is 3D, but now in general, I have whatever cube that I cannot draw. I have a 0, 1 cube. Then doing this under this assumption is exactly the same as doing subdifferential gradient descent. Okay, it's not subdifferential gradient descent, subdifferential method on this. So there are some connection, and that's very interesting. Yeah, because actually you can compute gradient here. You just say that for this discrete gradient, gradient is just something divided by h and then minus, right? You just say my discrete gradient, the h is 1, and then just move 1 unit left or 1 unit right, then you can have a gradient. Then you can apply first order method, and then
So just for the last inequality, so sun is the objective for the 0 norm.
2, 1, 2. Okay, 2, 2, 1, 2, 1. Okay, should be 2, 1. Because I forgot, I had to check. Basically, you can put a lot of things. Basically, if this is true, this is true. So any function that is 1 and 2, this can be replaced here. Yeah. So what does it mean? It means
that the greedy solution selects.
Yeah, the greedy solution will be as good as this. Yeah, yeah. I forgot the detail, but anyway, no time to explain this. Yeah.
Last thing I mentioned it, I think in my comments before, but yeah, you have to be careful because it's a bit confusing.
Yeah, I will. Yeah, I know. This is the hardest to explain, but I need to work on
No,
it.
yeah, it's an approximate NMF, and now it's an exact. So I think on the left you should put an exact one because it's also.
Okay, I will. We can talk about it offline. Time for lunch.
All right.
C'est bon?
Thanks a lot. Yeah, good talk.
Merci beaucoup, c'est tout.